to just show that it could be a revolutionary jump between the two. So this is a more readily understandable graph, I think. But you're looking at here all nano titanium dioxide articles as a percentage of all titanium dioxide articles. So you're seeing that in 1983, there was 0 of the titanium dioxide articles were pertaining to nano specifically, and whereas now we're up to like close to 40%, which is pretty big for articles. That means that it's a pretty established industry, and most of the new information is centering, or a large growing portion of the new information is centering on nano. And same thing with the patents as a percentage. It went from like 18% in the 80s to almost half of the nano patent, or of the titanium dioxide patents now are nano related. Okay, so tracking the share of nano in articles, and this is just a similar way to look at kind of the same information. This is all nano, and this is how much nano is titanium dioxide. I'm not sure what happened to my axes on this, but it starts with, so this is percentage, and then this is starting in, for us, for nano, like 86, and this is like 2004. So, all right, so this is showing you that nano is growing, nano titanium dioxide specifically is growing at a faster rate than all of nano, which maybe could imply to us that it's going more quickly toward commercialization than perhaps some of the other nano applications that are more basic science. And then same with patents, where the rate isn't so different, but the magnitude is. And I'm sorry that my mat conversion killed the axes, because that would be a lot more helpful for you. But what you can see is that by comparing the rate of nano titanium dioxide to regular nano, we are making the case that we might be able to use some of these same rates of increase. So what we said here is that the probable upper bound projection would be all of the titanium dioxide. And upper bound could even go up a little bit more than that, because there'll be unforeseen uses. That 3% could grow a bit with more catalysis. And what they have said is that the fastest that this could happen, based on applying the biotech increase, so we've got the most possible titanium dioxide out there using the fastest conversion rate that's ever been seen, so that's a good upper bound, would be by 2025. So from the Altair start date, and that is the 2003, from using the Altair patent to get us going, we'll see the compounded growth. And actual conversion obviously will be much more uneven than what this graph shows, because it'll be a little bit jagged as different countries come online, or different massive overhaul changes happen in infrastructure. But this is how it would calculate to get to the full 2 million metric tons for U.S. production per year by 2025. That'd be the maximum. So this then is just the titanium dioxide that's nano as a portion of that. And what we did then was try to translate, and this is more of what we'd like to do once we get better estimation techniques. But the take home would be, okay, so what? How much gets in the environment, how much stays? So based on different retention rates, and titanium dioxide is not shown to break down in the environment. It's just shown to stay and kind of accumulate in rivers and lakes. So based on different retention rates, how much would we see by 2025 out in the environment in met tons? And then more interestingly, when we get to those flows, where would it go in the environment, and what kind of information could we give to toxicologists about what the relevant concentrations that organisms might encounter? So this looks like could be anywhere from, at a 50% retention rate, which is pretty low, there could be 4 million metric tons in the environment accumulated of nano titanium dioxide by 2025. So the final conclusions, just to say, of this small part of our work is that if we had that full conversion to 2025, then we And assuming that we still have the U.S. production at 2 million met tons a year, then the cumulative environmental load could be anywhere from, as you saw, from that 4 million metric tons up to 12 million metric tons. And the job now is to say, to make that a much better estimation, compartmentalize that, look at a scope of our system that we're looking at now is, do we pick a single river system and decide where it's going to go and how it's going to transport within that and where it's going to end up, and then how do we give toxicologists a useful number to even begin testing so that you don't have to go all the way to, you know, LC50 or maximum load them. So I think that's all I've got prepared for you, and I'd be happy to take questions.
Yeah, we've got about 10 minutes for questions.